Have you ever followed a recipe and realized just how precise the cooking can be? Imagine if your 1 cup of flour is simply vanished or disappeared into thin air. Your cake, what will happen to your cake? Your cake would collapse, your bread wouldn't rise, your pasta would fall apart. Right? Here is a fascinating thing about chemistry. Nature follows recipes too, but with absolute precision. It follows with absolute precision. What does mean by that? In chemical reactions, atoms never vanish, they just rearrange themselves. Welcome to the world of chemical combinations where atoms follow rules far stricter than any other kitchen. Even your mom's kitchen won't follow that much strict rule. Nothing is created, nothing is destroyed, everything is transformed. That's not just good cooking, that's a good science. Okay, this is not a cooking class, this is a chemistry class. We are going to discuss laws of chemical combination. These 5 laws, we are going to discuss it today. And how well the question can be asked from this part, we'll also see. First thing first, law of conservation of mass. Ma'am, it is so tempting. Pasta is right here. Yes, I'll come to that part. Before that, what this man is thinking about. This man is called Anton Lavoisier. Law of conservation of mass states that in any chemical reaction, the total mass of the reactant is equal to total mass of products. In other words, matter cannot be created nor be destroyed. As simple as that. Right? Okay. What would be the real life example? I'm coming to that pasta. When you cook pasta in a sealed pressure cooker, let's imagine a situation like that. The total mass of the ingredients before and after cooking remains the same, even though the state and appearance has changed. Nothing is lost, it is just transformed. Water becomes steam, but it's all still inside the pasta after cooked. Okay, so how did he found out? How did he found out what is happening? Anton Lavoisier, a French nobleman and scientist, discovered this law of conservation of mass in the late 18th century. Before Lavoisier, scientists believed that in a mysterious substance called phlogiston that was supposedly released during combustion. If anyone knows what is this word is, let me know in the comments. Okay, let's move on. How did he found out? He took a sealed glass vessel containing a candle before and after burning, with a digital scale showing the identical mass reading. Let's say before burning it was 200 grams and after burning also it remains the same if that is a closed container. Okay. Despite the visible changes, the candle has burned, produced carbon dioxide and water vapor. The total mass remains exactly same. That's what he found out from his experiment. Here you can see the simple example for this law. In the reactant side, I'm having 4 hydrogens and 2 oxygen atoms. After the formation of water, there are 2 molecules of water has been formed with 4 hydrogen and 2 oxygen. Here also 6 atoms are there, here also 6 atoms are there, 4 and 2 hydrogen or oxygen respectively. Is it clear? But ma'am, where we are using it? I'm coming to that. Before that, I would like to give you an example, again the combustion one. When 12 grams of carbon combines with 32 grams of oxygen to produce carbon dioxide. So what is the mass of carbon dioxide? That is also 44. Right? So that is what this law of conservation of mass tells us. Okay. Coming to the point where we are using it. When designing the rocket fuel, engineers rely on this law to calculate exactly how much fuel is needed for a mission. The chemical reactions in the rocket engines convert fuel to oxidizer into gases. But the total mass remains constant, allowing precise calculations of thrust and velocity. From the 11th grade, we go on till the rocket science. Let me ask you a simple question. When iron rusts outdoors, it actually gains mass. Have you ever seen the rusted iron? Yes. Does this violate the law of conservation? Think about it. Are you saying yes or no? No. The iron combines with oxygen from the air, increasing the total mass of the iron object. The mass of the entire system is iron plus air, which remains constant. Okay. The next law we are going to talk about is law of definite proportions. Okay. So this law is proposed by the French chemist Joseph Proust. This law of definite proportions states that the chemical compound always contains the same elements combined in the same proportion by mass, regardless of its source or preparation method. This law is also called as law of constant proportion. In simple words, what I can tell you is elements combine in a fixed mass ratios to form compounds. Ma'am, you are saying something, but my concentration is on samosa. Okay, why the samosa is here? Because just like every samosa has the same potato to spice ratio in your shop, right? But not all the samosa taste alike, right? They are having different taste. Similarly, here also the elements are combined in the fixed mass ratio to form the compounds. Okay, let's take the simple example of making salt. Whether you make the salt in a lab or extract it from the seawater, it always contains sodium and chlorine, which is in 1:1 ratio. That is NaCl 1:1 ratio, right? The fun fact is that Proust was also a food scientist who invented the method to preserve food for Napoleon's armies. Okay, move on to the example. For the law of definite proportion, here I took 4 parts of hydrogen, 2 parts of oxygen. It combines to produce 2 parts of water, which is H2O. Okay. Water that is not 4:2 or 2:1 ratio, then that won't be forming water. So what is the percentage of hydrogen, percentage of oxygen present here? So 2 hydrogen atoms, that is 2 AMU, 1 oxygen atom, that is 16 AMU. So the molecular weight of water total that become 18 AMU, atomic mass unit. Percentage of hydrogen by weight, which will comes out to be 11.11. Percentage you can calculate it by 2 by 18, that is 11.11, and 16 by 18, which is 88.89. Okay, so whether you are taking the water from Himalayas, whether you are taking it from Bay of Bengal or from Pacific Ocean, anywhere, or from your RO, anywhere, water remains with the same ratio. Okay, it won't change. Then, what kind of problem you can expect from this part? Your 5-gram sample of calcium carbonate decomposes to produce 2.8 grams of calcium oxide and carbon dioxide. Calculate the percentage by mass of oxygen in calcium carbonate. So what is the reaction happening over here? Calcium carbonate gives calcium oxide and CO2. It is producing 2.80 grams of calcium oxide and carbon dioxide. First, we have to find the mass of CO2 released, which will be 5 gram. From the law of conservation of mass, I just combined those two principles here. From 5 gram, the total formed also will be 5 grams. So the CO2 will be 5 minus 2.8, which comes out to be 2.20 grams. Okay, right? Next step. We are going to find the total oxygen in calcium carbonate. 3 oxygens are there, right? So the molecular mass of calcium is, calcium atomic mass is 40 plus 1 carbon 12, 3 oxygen, that is 3 into 16 comes out to be 100 as a molecular mass of calcium carbonate. Okay, so now we are going to calculate mass of oxygen from this. So 3 into 16 divided by 100. Mass of oxygen, which is 3 into 16 divided by 100, thus that comes out to be 2.40 grams. Okay, then we are going to calculate the percentage. So total, I am having 2.40 grams of oxygen out of 5 grams. So the percentage of oxygen, which is 2.40 divided by 5, that comes out to be 0.48. Since they are asking for the percentage, multiply into 100, that is 48%. No matter how you create a compound, its composition by mass is always the same. Okay, moving on to the next law, that is law of multiple proportion. From each one of those law you are showing a food item. Yes, that is true. Let's see what this law says. The law of multiple proportion was proposed by John Dalton. When two elements combine to form more than one compound, the mass of one element that combines with the fixed mass of another element in a simple whole number ratio. This is too long. I can understand. I can hear you. Let's say what it is going to say. What it is saying is that, let's say the chef is using 1 spoon of chili powder and 2 spoons of chili powder for the same amount of noodles. What will happen? The taste will change, right? But the other ingredients are same. Chili powder remains as chili powder, but the quantity matters, right? That's what he is also saying. The fun fact is, Dalton has a rare condition called color blindness. Despite his visual challenge, he saw the patterns in data that others missed. So, you are also unique, but you should be in the field. Okay, let's see what it says in detail. Here I am having H2O, water. Hydrogen and oxygen ratio is 2:1. But still, hydrogen and oxygen is there. Okay, there is another compound called H2O2. Water is H2O. This is H2O2, which is called hydrogen peroxide. Okay, this is entirely different from water. All those properties. Although this is liquid, colorless liquid, but still the properties are different. You can't drink it. The formula is H2O2. The ratio of hydrogen and oxygen is 1:1. That's why I told you in the last law also, it should have a definite ratio, and if that is combining a different ratio, then it would be forming a different compound. Okay, the same example you can take for same principle or law, you can take for nitrogen and oxygen. NO2, which is having 1:1 ratio, NO is having 1:1 ratio, NO2 that is having 1:2 ratio, N2O, this is laughing gas, that is 2:1 ratio. You can take an example of carbon and oxygen as well. It can form CO2 and CO. The ratios, you know, right? 1:2 ratio and 1:1 ratio. Can be asked from this law. At the same temperature and pressure, 50 ml of gaseous hydrocarbon requires 60 ml of oxygen for complete combustion, producing 45 ml of carbon dioxide and vapor. Determine the molecular form of hydrocarbon. Okay, so what is hydrocarbon? Which is just having carbon and hydrogen. For now, let's understand that is what the hydrocarbon is. Okay, hydrogen and carbon. We'll see more in while we are talking about organic chemistry. Okay, so what is the values given over here? That is 50 ml of gaseous hydrocarbon requires 60 ml of oxygen, producing 45 ml of carbon dioxide. So the water vapor formed, the volume is not given, but still that is formed as a product. We are going to assume all gases measured at the same temperature, pressure, and the volumes of gases are proportional to its moles. Okay. So CX and HY, I don't know the number of carbon and hydrogen in hydrocarbon, plus O2 gives CO2 and H2O vapor. Okay. So amount of CO2 produced, which is 45 ml, and amount of hydrocarbon used, that is 15, and oxygen used is 60. So 45 ml of carbon dioxide is from 3 parts of hydrocarbon, right? Since the 15 ml of hydrocarbon is giving 45 ml of carbon dioxide. So which I can taking that as 3 CO2 molecules must have been formed. So yes is 3. Okay, let's consider about oxygen. So each oxygen molecule contributes to oxygen atom, right? So the total number of oxygen atom in the product side, that is 4. 3 into 2, 6, 6 plus 1, 7. The total number of oxygen, how much it is used? 60 ml. So which means that 4 parts of hydrocarbon equal to this 60. So which I am taking that as 4 O2. That is 8 oxygen atoms. Right? 8 oxygen atoms, 4 molecule of oxygen. Now we are going to balance it. CO2 uses 3 oxygen atoms. So total 6 oxygen atoms, total 6. So remaining 2 oxygen must be there. That goes to H2O, which is 4 hydrogen, which makes Y is equal to 4. So the compound must be C3H4. So if you don't understand this problem now, don't worry. If you are in the beginning of the 11th grade, if you are not able to understand this problem now, don't worry. But I assure you that, I promise you that at the end of this series, some basic concepts of chemistry series, we are going to understand this problem. Okay? So don't worry. Don't get demotivated. You are just right. Okay. Moving on to the next law, Gay-Lussac's law of gaseous volumes. So what he says is, when gases react, they do in simple whole number ratios. So what is that? let's say I'm taking H2 and O2. The same simple example. H2, 2H2 plus O2 gives H2O. So the two volumes of hydrogen gas, one volume of oxygen is combined to give two volume of H2O, right, which is in 2:1:2 ratio, right. Now once again read the law. When gases react, they do so in simple whole number ratio, right. We already know if that is not in a simple whole number ratio, then the product will be different. What will be the respective volume of hydrogen and oxygen consumed in liters if 20 liters of H2O produced in the following reaction? The next law, that is Dalton atomic theory. So the same man, Dalton, proposed this theory. What he says is all matter is made up of tiny indivisible particles called atom. So he just combined all other laws, I would say, because since atoms cannot be created nor be destroyed, the total mass remains the constant in chemical reactions, right? Okay. Then the second line, atoms of the same element are identical in mass and properties. If I'm taking oxygen which is equal to oxygen, nitrogen which is equal to nitrogen, right? Atoms of the different element have its different mass and properties. Okay, nitrogen which is not oxygen, correct? Then compounds are formed when atoms of different elements combined in the fixed whole number ratio. That's what we said in definite proportion, law of definite proportion. Then the fifth one, chemical reactions involve rearrangement of atoms, but atoms themselves remain unchanged. The rearrangement of atom happens, but still they remains unchanged. Okay. From oxygen molecule, oxygen can combine with hydrogen, but oxygen will remains as a oxygen, right? Okay. Although he has explained everything, but still our modern theory is saying atoms are divisible, right? We do have protons, neutrons and electrons. But the second thing he said, that is all the atoms of same element remains the same, but we do have an isotope exist. This third one, what he said for the reactions is not holds true for the nuclear reactions. Nuclear reactions can transform the elements. These are the examples, these are the practice problems you can practice from this part. If you can't do these problems for now, that is totally fine, totally understandable. But end of this series, first chapter series, you will do it. Okay, mark these questions, take a screenshot of it. But we are going to solve it. You can solve it after the upcoming classes. If you need more practice problem, I'm attaching the link in the description. You can just purchase the daily DPPs of every session and you can do the practice for entire year along with the DPPs, mock test, formula sheet and whatnot. Okay, so stay tuned for the next session of some basic concepts of chemistry. Thank you.